All right, so now we're going to talk about this 1214 addition, and we're going to talk about what we can do with it. Why is it valuable, or why is it interesting? And we're going to consider it from an energy standpoint, and we're going to look at the intermediates, right? So recall, of course, that if we get a 1214 addition, we can get addition of the HBr at the 1,2 position, right? There you go. Or at the 1,4 position, right? Watch out for this double bond, by the way. This double bond, the double bond didn't move. It was really the pi electrons that moved. So if this is the 1,2 addition, and that's going here, and this is going here, these electrons over time are coming here, right? So these electrons are these electrons. And it's also these electrons for when they didn't go there, all right? So watch out for that. Interestingly, at cold temperatures, we can push the 1,2 adduct. Or at warmer temperature, this is about body temperature 37 degrees Celsius, we can get the majority to be the 1,4 adduct. Why? Okay, so let's look at the energy diagram to figure this out. So, first of all, if you're talking about the energy diagram for the 1,4 addition, it's going to be the red curve. If it's the 1,2 addition, it's the blue curve here. All right, again, can you see that they're both going to start out in the same place, of course, right? Because they're starting out with exactly the same thing. So this is the energy of the transition state, the first transition state, which we'll call star, or rather double dagger, right? And here's another transition state, let's say transition state 1 and double dagger 2, transition state 2. So what happens is, let me draw this dying here like this, and you get these attacking that, and it's going here, right? So the energy of this first transition state, it's going to look like this. Can you see that? I drew that right over top of that. Oops, that's not a plus. That's not a minus yet. It's a partial minus because it's starting to get its minus. And this double bond is still here, and this is going to be a partial plus over here because it's starting to lose its pi electrons. Okay, so this is a picture of the transition state. This is double dagger 1. Can you see that? Okay, so now the intermediate now looks like this, but really it's not fair to draw like that because it's really a resonance, right? So the other resonance structure is like that. So the real intermediate is the combination of those two, which looks like this. That's a hash line, not a very good one. Okay, there you go. And that's got a partial positive, and this has got a partial positive, right? So the resonance hybrid, that is the structure, how the structure really looks, is always a mix of these structures. And it looks more like the one that's more stable. Okay? So can you see that if this is atom 1 and this is atom 2, in one of these structures, atom 2's got a charge, in the other one it's neutral, and so we're going to say it's got a partial positive charge, right? In the others, let's see, atom 4, in one of the structures it's neutral, and one it's charged. So it's also going to have a partial charge, right? Which one of these is more stable? Which one is more stable? Can you see that it is this one? A lot too many arrows here, isn't there? This is the one that's more stable because it's a secondary carbocation and it's allylic, right? This one's allylic, but it's primary. So this one's the one that's more stable. So if I were to ask you which of these partial charges is bigger, what would you say? Again, the transition, or the real structure, the hybrid, the resonance hybrid, is a mix of these two, and it looks more like the one that is more stable. So which of these partial charges is bigger? Okay, I'm not going to answer that. I'm going to leave that with you. Good question. All right, so that's the reason why they start out the same, right? You see that? Now, the in order for, since this one's more stable, right, it's going to have a lower, well, actually, no, that's not the reason why. The book says, and everybody agrees, although it's a little hard for me to believe, that the reason why this one has a lower activation energy is because the bromide, when the hydrogen gets added to here, the bromide happens to be right by there, okay? And so this is called proximity effect. Don't write that down. I don't think it matters. It's called a proximity effect. And that is the bromide's right close by anyway when this happens. So bam, there it goes, right there, okay? And that's gonna give you the blue curve, which gives you this one here, right? Can you see that? Okay? So the transition state for the blue one, I'm gonna draw the transition state for the blue one, you draw the transition state for the red one. And let me go here. See, I drew this down here. I drew this as my 1 carbon. Here's my 2. Here's my 3, and here's my 4. 1, 2. Are you okay with me reorienting this molecule? I'm just doing it to make it easy for myself, right? So if the transition state here, it's going to be my hydrogen is here, and the bromide is attacking. For the blue one, the bromide is attacking here, right? So we're going to have the formation of the partial formation of a bond. And so what we have is now the transition state is going to look like this. Oops, too many carbons. Oh wait, let's just make that a hydrogen. Right? Where this has got a partial minus, and this is a partial plus. Look, my handwriting just got really neat there. Okay, I wish I could do all of it like that. So that's what the transition state looks like. Can you see why? Because the transition state looks somewhat like the starting material and somewhat like the ending material. And it looks more like the one that's more stable, so it's going to look more like this, okay? But this is the picture of the transition state where you've got a bond beginning to form. There's also some lone pairs of electrons here, a little hard to draw with this marker. All right, so can you see why, you really can't necessarily see why the activation energy is lower. You need to draw the transition state of this guy. Draw the transition state of the 1,4 adduct being formed. Draw that's this one right here, okay? And then compare those two, and you'll know that this one is the lower one in energy because, well, you see, it's lower, right? Okay, now since it's a lower transition state, it's going to go faster, plus the proximity effect. It's going to go faster, and if you have sufficiently cold temperatures, you don't have enough energy to get up over this hump, right? It takes heat to get over this hump. And so remember the Arrhenius equation? So the rate of the equation is proportional, not directly proportional, but it tracks with, let me say, it goes with the temperature. The rate of this equation goes with the temperature. The temperature is exponent. But all right, now look down here. I think on the next slide I need to sneak peek at the next slide. Just give me just a moment here. Yeah, I already drew the transition state for one of them. You need to draw the other one. I need to take a sneak peek at the next slide. The 1,2 addition should occur more often regardless of temperature. Why? Because we just said so. It's proximity effect 2, by the way. We just said that. We just said why about that. Okay, now explain how high temperature yields one product while low temperature yields the other. Can you see why high temperature is going to yield this one? Okay, and the final question, do I have this in the slides? No, I don't. The final question is which of these is more stable? Oh, you can tell. The 1,4 adduct is more stable, right? Because it's down here. Which is more stable? The 1,4 adduct. Why? I'm pretty sure the book does say, but try to answer that before you look at the book. Why is the 1,4 adduct more stable? And then we can see why it's more stable. It's because it's down here. But you tell me by looking at it, why is it more stable? All right. Now, predict the major product for the following reactions. And I'm not going to give you the answer for that. I'll give you the answer in class if you ask. But you bring your notes to me. If you ask that, bring me your notes and show me what you have for this. Okay. Now, we need to look at this. Klein has it. I don't think it's not the most important thing we're covering here. Many polymerization reactions rely on the 1,4 addition. Draw out a reasonable mechanism for the cationic polymerization of isoprene. Show how that works.